All right, guys, this is worksheet 1. We are covering chapter 3 out of the Glencoe book, which is chapter 5 out of our book. This is exponential functions, okay? They talk about some vocabulary here. I found it interesting. It says in chapter 2 you studied power, radical, polynomial, and rational functions. Well, that is what we just did in chapter 4 in our book, okay? These are examples of algebraic functions. I don't know this terminology, but it says exponential and logarithmic functions. These are considered to be transcendental functions because they cannot be expressed in terms of algebraic operations. In effect, they transcend algebra. I just felt like we were so smart. Do you remember when we did logarithms last year in Algebra 2 vaguely? Okay. When you rewrite an exponent sentence as a log sentence and the log is a rewrite, okay? Yes. That's what they're talking about, that it's not, it's a new kind of thing for us. This transcends your basic adding, subtracting, multiplying, and dividing. All right, we are going to talk about exponential functions. And we need to know the difference between a power function and an exponential function. An exponential just means x is in the exponent. So if we have some kind of equation, let's see, get a pen here. If we had, 6x to the third minus 2x plus 9, that is some kind of a power function with some garbage on the back here, but we have an x to some power. An exponential function is when the x is in the exponent. So if we had 2 times 1/3 x, okay? When x is in the exponent, then it's an exponential function. All right, an exponential function has a base b, and the general form is a times b to the x, where x can be any real number, so that's telling us the domain is going to be all real numbers. And it says a and b have to be real numbers. A can't be 0, because then we just have y equals 0. And b has to be positive, and when they write it as a negative, we're going to rewrite it. And b cannot equal 1. What that's saying is when you have this, it really means the opposite of 6 to the x. Okay? You always have to do exponent powers first and then do the opposite anyway, but that's why it's saying b has to be positive. All right, moving on. Because if we just had y equals 2 times 1 to the x, no matter what we put in for x, we're just going to get 1. And then 2 times 1 would just be 2, so we just get a horizontal line. So it's really not an exponential function then. Good question. Anybody else? All right. This is a graph of an exponential function. I'm not going to go through step by step here, but 3 to the x, if you put in a 1, you get out a 3. They didn't even put in a 1? Okay, you put in a 1, you get out a 3. You put in a 2, 3 to the second is 9. Put in a 3, you get out a 27. Okay. Put in a negative 1. 3 to the negative 1 means 1/3. Do we all remember fractional exponents? Well, that's not a fractional exponent, a negative exponent, sorry. 3 to the negative 2 is 1/9, and so on. It looks like this when you plot those points. The domain of any exponential function will be all real numbers. The range, if you look over here, bottom to top is 0 to infinity, and it does never actually hit 0. It has an asymptote at x equals, or I'm sorry, at the x-axis, which is y equals 0. It will always cross the y at 1 unless we have a stretch, because anything to the 0 will be 1. Does that make sense? Okay, if we multiply out in front by a stretch, then it will change. But this will cross at, I didn't do a very good job, sorry. That is 0, 1. I made a really big dot, so it looks like 0, 2. All right, This graph increases as you go left to right. And if you look at the chart, look at the numbers. Are they increasing as you go left to right? Okay. The end behavior, we have to talk about this. We don't have to use the limit symbol again, but we would say as x approaches negative infinity, we can't use our end behavior equations like we did in rational functions because both ends were approaching one thing. Today the ends are doing different things. The left end is getting closer and closer to 0, so we write it that way. The right side, when x is big, is getting, what's it doing on the right? Yeah, it's going up to infinity, exactly. It's going up forever, okay? Those are the kinds of things it's going to ask us to do about basically every graph we look at. So here's another example. They have 2 to the negative x. The big thing we want to talk about here is that 2 to the negative x is really 1/2 to the x because it's 2 to the negative 1 to the x. 2 to the negative 1 is 1/2. Everybody okay? 2 to the negative x is 1/2 to the x. It's getting smaller as it goes to the right. It is decreasing because if you put in a negative here, say we put in a -2, the opposite of -2 would be 2, so 2 to the second would be 4. So on the left side where the negative x is, it's a bigger number. As you go to the right, when you put in a 2, 2 to the -2 becomes 1/2 squared, or 1/4. So it's getting smaller and smaller the bigger the x value. Yes?
Is 0, 1 always going to be 1?
Unless there's a stretch, yes. Because anything we do to a 0 power turns into 1. When they start throwing things out here like this, then it's not anymore. Then it's going to be through 0, 3 because of that number out front. Good question. Yes?
So, is there any way to find domain and range on your calculator?
You can graph it and look at the graph,
Yeah.
but that's it. Nope.
Oh.
All right. We're going to go through these 3 quickly, and I have them 1 to a page here so we can write a little bit bigger. 6 to the negative x is really 1/6 to the x power. So which shape is it going to be? Well, if we put in a 0, what are we going to get out? Okay, if we put in a 1, we're going to get out 1/6. If we put in a -1, we're going to get out a 6, because that will flip it over. So at -1, it's up at 6. At 0, it's at 1. And at +1, it's at 1/6. So it is like the one we just did a second ago. Just going this direction. All right. Can anybody tell me real fast the domain and range? Okay, and it doesn't ever actually hit 0. If you trace out far enough, your calculator will round it to 0, but it doesn't ever actually become 0. End behavior on the left, as x gets more and more negative, what is this graph doing? What? It's going up, so it's positive infinity. On the right, as we go off to the right, this graph is getting closer and closer to 0. Unfortunately, mine looks like it's going to go up again. It's supposed to be getting closer to 0. That's my fault. Its intercept is at 0, 1. It has an asymptote at the x-axis, which is the equation y = 0. Does that cover everything that's up there? Domain, range, intercepts, asymptote, end behavior. Increasing or decreasing? What is this one doing as you go from left to right? Decreasing. All right, on 1B, I'm actually not going to list all of this stuff just because I want to, oh, maybe we will, quickly. What's going to happen here? If you put in a -1, you will get out a 1/5. If you put in a 0, 5 to the 0 is Put in a 1, 5 to the 1 is. So negative 1 is a very small number, 0, 1, 1, 5. It's going this direction. Okay, so the domain and range are the same as the one we just did. I'm just not going to bother to write them down. I don't care if you do. The asymptote, the graph looks bigger, but is the asymptote different? I lost my M in there. No, it's still the x-axis, which is y equals 0. It's still crossing at 0, 1. It has no x-intercept, only a y-intercept. Is this one increasing or decreasing? Increasing. And this time the left, whoops. That didn't make any sense. It is the left, but I say as x approaches negative infinity, what's happening? It's approaching 0, yes. As x gets really big, y is getting really big too. Don't tell Miss Heimer I'm cheating, because you're supposed to always do y first and write it in f of x form. So you would say y approaches infinity as x approaches infinity. This is the way I think about it, so that's the way I'm going to write it, okay? But I think if you decide to take calculus, you could handle switching the order around, right? All right, this one. This is a shift, guys. What's going on here? It's on the whole function, so it's going to go up 1. But otherwise, which one does it more resemble, 1a or 1b? 1a. It is decreasing. It's going to look like this. The asymptote is going to be up here at 1. And it will cross at what? When you put in a 0, what is 1/4 to the 0 plus 1? Yeah, it's going to be 2, because this is going to become 1 plus 1 is 2. All right, so we took care of the asymptote and the intercept on the graph already. The domain and range, that does change a bit. The domain is still negative infinity to infinity, but the range is what? Yes, 1 to infinity. Off to the left, it's getting very big. Off to the right, what's happening? It's getting closer to 1. What did I leave off? The asymptote was at y equals negative 1. The intercept was 0, 2. Increasing or decreasing? All right, did we pretty much cover everything we needed to know there? Am I remembering right that at the bottom of this page it gives an overview or not? Yeah, at the bottom here it talks about that a growth equation is when you have a b value greater than 1. Okay, a stretch out front, so if you have something like this, the a will change the intercept, but as long as you don't have anything out front, b to the x with a b value greater than 1 will look like this. A b value less than 1, but positive, will be decreasing like this. Okay? And again, the a does change things. It can reflect all kinds of stuff. All right, they want us to talk about the shifts. And I'm good if we just go over them very quickly here. 2 to the x plus 1. Well, 2 to the x looked like this. What would a plus 1 on the x do? Left 1. Okay, this will shift the graph 1 unit to the left. So it's down here. The blue is the original, the red is the new one. Part B says 2 to the negative x. What did we learn that a negative on the x does? A negative out front flips it over the x, but an x-axis, but a negative actually on the x, inside on the function, does what? Reflects it across the y. So 2 to the x looks like this. 2 to the negative x should look like this. Is that what we said when we did a 1/2? was doing that, right? The blue one? So 2 to the negative x and 2 to the x are reflected across the y-axis. What's happening on C? It is a vertical stretch. Yep, and the negative flips it over the x because it's a negative out front. So it says reflected over the x-axis because of the negative out front, and vertically expanded by a factor of 3, in other words, vertically stretched. All right, so in this case, it stretched down 3 times as fast, which is why it's crossing here. Everybody okay with those? All right, so describe the translation and then do a rough sketch. And I won't make us do all the crazy business about what it does, but 4 to the x is a growth function that looks like this. What is 4 to the x minus 2 going to do? So it's not on the x, it's on the whole function, so it's actually going to go down 2. So what will change? Yes, the horizontal asymptote is at y equals negative 2. Did I call that a vertical asymptote earlier? I feel like I did. I shouldn't have if I did. If this was crossing at 1, where's it going to cross now? We'll put a 0 in if you need to. 4 to the 0 will be 1, minus 2 is negative 1. Okay, everything's shifting down 2, and there's the shape we will have. For 2b, 2 things are happening. This negative out front will reflect over the x-axis. But what is the plus 2 here going to do? Shift it which way? Yep, left 2. So, if this was our original function, okay, not the new one, the new one is going to reflect upside down and then shift left 2. So we got to figure out where it crosses here. When we put a 0 in, we get negative 4 to the second. What does that become? Exponent first. 4 squared is 16. The negative makes it negative 16. So what did I put in? A 0 when I got that out? This is clear at 0, negative 16. Did I do that right? That seems really... 2 plus 2, yep. All right, the asymptote eventually is still going to approach 0 here because we did not shift it up or down. Okay, if we put in like a negative 5, this becomes negative 4 to the negative third, which is negative 1/64th, so it's getting very, very small. Okay. What about this one? Anybody know the last one? First of all, here's our original, whoops, sorry, I don't know what I'm doing dotted axes for. Here's our original function. It is a vertical stretch, and what is the negative inside here going to do? Reflect over the y. Yes. So it's going to go this direction. And it's stretched up 2, so it's actually going to go very quickly up like that. If we put in a 0, we would get out what? 2, yes. And the asymptote is still y equals 0. If we put in a 1, we'd get out a 1/2. If we put in a negative 1, we'd get out an 8, I think. All right, anyway. Transformations still hold true. This is very important. In calculus, you'll talk more about this because it's actually the limit of this problem. And I'm not going to take time for us to type on our calculator, but if you put in 1 plus 1 over 1, all to the 1, you get out 2. But if you put in 1 plus 1 over 10, all to the 10th power, you get out this decimal. If you put in 1 plus 1 over 1,000, all to the 1,000th power, gets this. The bigger the number that you put in for x, the closer this number approximates to a number that occurs in nature called e. May surprise you to learn that most real-world applications involving exponential functions, the base is not a 2 or a 10, but an irrational number called e, which is the natural base. All right. We talked about this last year because we did things like, remember the interest formula for continuous interest? And we also talked about natural logs, which undo base e. Those things sound vaguely familiar, okay? So e is actually defined by the limit of this problem. I'm sure you were all dying to know where e actually came from, okay? It's the limit of this. All right, this is the graph of e to the x. So it's just an exponential growth with like 2.7. All right, let's talk about these really fast. What would a 4 do on the x? Almost. Remember, anything to the x does the opposite. So it's horizontal shrink or compression. All right, what about a negative on the x and then a plus 3 at the end? The plus 3 on the end would do up 3, and the negative on the x reflects across the y-axis. These are down here, if you want to look at the graph. 1/2 in front, is that going to be a vertical or horizontal change? No, on the x itself is a horizontal change. Out in front, it is a vertical change. And the 1/2 compresses it vertically. In other words, it shrinks it. Okay? And you will notice it's very hard to tell. If you graph e to the x and e, or 1/2 e to the x on your graphing calculator, you will see almost no difference. Okay? If you looked in the table, you would see a slight difference in values. All right. Really quickly, just tell me what these do. I don't even care if we don't sketch them. I'll sketch them if you want. You can sketch them. What is reflect over? So instead of doing this, it's doing this. What does this one do? This one is down 5 because it's not on the x, it's on the whole thing. So the original e to the x was doing this. This one is going to be down here. Okay, where the asymptote would be at y equals -5. 3 e to the x does what? Vertical stretch, so your basic e to the x would be doing this. 3 e to the x would cross sooner because it's being stretched up. It would cross at 3 here. Okay? All right, exponential growth and decay. A common application of exponential growth is compound interest. Suppose an initial principal P is invested in an account with an annual interest rate R, so they're saying P is your initial amount, R is your interest rate or percentage. If the interest is said to be compounded, it is reinvested annually. At the end of each year, the interest is added in and the sum is a new principal. If you wanted to compound it quarterly, monthly, or even daily, you would put the number of times you were going to compound it in as n. The interest rate gets split out over those compoundings, and the exponent becomes nt, or the total number of compoundings. Do those two formulas look familiar from last year? okay? This is basic exponential growth, which they do not stress. They assume you already know that this formula is exponential growth. How would we make it decay? No, instead of 1 plus r inside, it becomes 1 minus r, okay? This is the compound interest formula. If you have a TI-83 or older calculator, you don't need extra parentheses inside, but when you do this exponent of NT here, you need parentheses around those, okay? If you have the newer operating system that puts it up in a little box for the exponent, you don't have to worry about it. But if you have the older one, you have to do to the power of with little parentheses around the N and T. And again, R is a decimal. The rate has to be changed to a decimal. Let's do some examples. I'm not going to have us spend a lot of time typing these because we'll do one towards the bottom of the page here, but it says, Christy invests $300, 6% interest, annual interest. What if it's compounded semi-annually? So it's split out over 2 compoundings a year, and she's going to leave her money in there 20 years, so this will be 2 times 20 or 40. They typed that all in and got this amount. Are we okay with just believing them?
Yes.
Okay. Monthly, what would change?
It would change the
The
bottom.
2 places that I wrote 2s instead of semi-annually would become, both of them would become 12s, okay? And there's example here. She got a little more money. Why did she get more money?
Because you have more.
They put her interest in and she earned interest on that interest because they put it in faster, okay? This table, guys, please look at this. It's on the next page, I think. This table shows if you had put in, Christy had put in $900 and left it there for 20 years and it was only compounded once a year, she would have wound up with this amount. If it was compounded monthly, she would be up to $993. Hourly, she'd be up to $996. Now, is there much change down here once you go monthly, daily, hourly? No. But there is a way to do this without getting closer and closer to an amount. It's called continuous interest. Okay? The continuous interest formula can be derived algebraically. I didn't bother to copy that part of the notes for you. I figured you weren't too excited about deriving the formula. Okay? So the continuous interest formula is here. Does this look familiar? I just put it on the board a minute ago. Okay? But it says the interest rate is the decimal, and this is an exponent. I didn't write it small enough. Doesn't look good right there. Okay. So let's do an example using that formula. It says Christy were to put her money in $300 and she was going to leave it at 6% for 20 years. You would do this. And it would be $996.04. Can we go back to the chart real quick? Is $996.04 very different from hourly? It's not that much differently than daily, right? But she didn't have to use that same complicated formula. She just got to use this shorter formula. All right, can everybody do this question, please? And type it in your calculator, because I need to know if we're getting this correctly. $1,000 is invested at 8% per year, compounded continuously. Okay? So we're going to use E. To the power of, the rate is 8%, 0.08, and we're going to leave our money in there 10 years. How much? Okay. I'm sorry, I should have pulled up the calculator here. The E key that I would use for that question is on the left-hand side of your calculator. This ln, I would do second ln because when you do second ln, it brings up e to the power of, and if you're using an older calculator, it even brings up e to the power of with a parenthesis. So it saves you touching all those keys, and it just does it automatically when you do that one. All right, and then we did 0.08 times 10. Any questions?
Yeah, what's the other key?
That's a good question. It is above the divide. Yes, above the divide. If you just did second divide, you would also get an E, but then you would have had to hit to the power of parenthesis, blah, blah, blah. All right. This is important. Please be paying attention here. The exponential growth or decay function looks like this. Okay? Your original amount times 1 plus or minus, depending if it's growth or decay, some value. This is a percentage. Okay? It could be, it's growing 100%, but R is your rate and T is time, and that will give you the amount after a certain amount of time. Again, it's minus if it's decaying. The exponential, continuous exponential growth is original amount. So let me write that as original. Okay, apparently I can't write it as original. Times E to the RT. And if it is decaying, your R value will be negative. Just like we put in 1 minus R over here, this will be a negative R value if it says it is decaying. This is continuous.
So you can say plus or minus.
Sure, you could write a plus or minus on that R, yep.
So for the geometric sequences that we did at the beginning, first chapter,
Yes?
like the sum theorem, because it's like 1 minus r to the x squared, does that have to do anything? That's how they derive that equation.
I have to think about that. Okay. This is, it is related, yes. This is a question about the population growing annually, and it wants two different amounts if it's growing, how long, for 10 years or 20 years. Again, it would be 1 plus 1.42% annually would be 0.0142, okay? And it said there was originally 110 million people, and if we wanted 10 years or 20 years, we'd put that in the exponent. That's how they got those answers. I'm skipping down. It says here, blah, 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 continuously, okay? If you were doing continuously, you do 110 e to the 0.0142. Everybody knows where I'm getting 0.0142? 1.42%, move the decimal back twice. Okay, and then we would put times 10 for 10 years and 20 for 20 years. They did it twice. They did everything twice. 10 years, 20 years, 10 years, 20 years. All right. Let's do our example right here. And I don't want to take time to do it twice, so let's go with 10 years. Okay? Let's do this one time with 10 years. If we have a current population of 12,426 people, and our town is, what's happening? It's declining, so what's going to go in the parenthesis here? 1 minus 0.06. We're going to do 10 years. So type that in and see what you get. I could also have used what instead of 1 minus 0.06? No, I could have used 0.94, right? 1 minus 0.06 is 0.94. All right, I got 6693 if I round, because it's people.
We can have a third of a person.
All right. And continuously means I'm going to do 12,426 times what? E to the negative 0.06, because it's decaying. 6% of the people are leaving, times 10 years. 12426 e to the negative 0.06 times 10. No? I just rounded to a whole number. Did I do something wrong?
I typed it in wrong.
Okay. Everybody good? All right. I had the same question. I thought that continuously declining would be less people because it's more interest. It grows faster. I don't have a good answer for that. I'll ask Ms. Falzone if she can explain that to me, because, you know, when you put your interest in continually, it grows, your money grows faster. So why wouldn't this be decaying faster? I kind of had the same question. All right, I want to get through this example quickly, guys. This says this, what time are we done? 35? Okay, so I have plenty of time, so please pay attention. I hear a lot of chatting. This is a very important issue that it says if we have the number of reported cases of chickenpox in the United States from 1980 to 2005, we need to find the growth or the decay rate. How fast were the cases dropping? So we would use our equation, our original amount, 1 plus or minus some rate. How many years did this occur, guys? From 2005 minus 1980 is 25 years. So we're going to go to the 25th. And after 25 years, it was down to what? 32.2 cases. All right, is everybody okay with what I did? Now, R should come out negative, right? I could have put minus in there. I just left it plus. It's going to come out a decay because the cases went down. What is the first algebraic step to solving that equation? Dividing, okay? So we have 1 plus R to the 25th equals 32.2 over 190.9, and I'm just going to leave it like that for a minute. Now, if that was squared, we'd square root. If it was cubed, we'd cube root. And it is possible on your calculator to do a 25th root. But does anybody remember the easier way, instead of going to that 25th root, what power is a squared? A square root is really a 1/2 power. Remember this? A cubed root is really a power of 1/3. So we want to do both sides to the 1/25th power. Would that cancel out that 25 up there? Okay, so we're going to do both sides to the 1/25 power. So I want you to type 32.2 over 190.9 in parentheses to the power of 1/25th. .9313 if I go out 4. Okay, and what was left on this side was a 1 plus R. So if we subtract 1, what do we get? Negative .069 we'll go with. So about 7%. It dropped about 7% per year. The number of chickenpox cases dropped about 7% per year. It's when they started vaccinating people for chickenpox. All right. Guys, I got a couple minutes left, please. If we wanted to know when the cases would drop below 20,000, we would say, well, it started at 0.9. It is going down 1 minus 0.069 every year, and we want to figure out how long until it drops below 20,000. And these were thousands of cases, so we want to know when it hits 20. So we would graph this, and it is going down. We would see the intersection point where it hits 20. They found 31.6 years after what, though? Well, I used this number, and that was what year? 1980? So can somebody add 31.6 and 1980? Okay, so 2011.6 or sometime during 2012, or during 2011 going into 2012, it should have dropped to 20,000 cases. Right, that's the only way we know how to solve that kind of a problem when we're looking for the exponent at this point is graphing. We're going to learn to use exponents to solve that kind of problem eventually. Or, I'm sorry, logarithms. Logarithms. All right. You should be working, guys, you should be working on tonight's worksheet 5B, worksheet 6, A and B, and 7B. Please refer to the pink sheet because the pink sheet says you're allowed to cross out these problems, and it says skip worksheet 7A until later in the chapter, etc. Okay? So don't just go through and do everything. Just look at the pink sheet like you normally would. This is your book.